As we discussed in the previous section, a critical piece of a titration is having a way to signal when that equivalence point has actually been reached. For acid-base titrations, we want to use an acid-base indicator whose transition point, in other words, the point at which it's actually changing colors, is going to happen when the equivalence point is reached. So we want those 2 points to correspond with each other. Acid-base indicators themselves, remember, are just weak, typically monoprotic acids whose conjugate pairs display different colors and typically vibrant colors when they're in their protonated and deprotonated states. Here's an equilibrium for a general acid-base indicator. As we can see, there's a protonated state and a deprotonated state. And what's special about acid-base indicators is that this protonated and deprotonated state will have different colors. So we can see an observational change when the equilibrium changes position. The protonated state is going to be favored when the equilibrium lies to the left. This will happen when the indicator is in the presence of acid, as the increase in hydronium ion concentrations from the acid will drive the equilibrium to the left. The deprotonated form of the indicator will be favored when the equilibrium position lies to the right. This is when the indicator is in the presence of base, as the base will neutralize the hydronium ion, lowering its concentration and driving the reaction to the right. Where this transition actually occurs, at what pH ranges, is going to depend on the Ka of the indicator itself, which we can see the expression here. As we can see from the equation above, the concentrations of the conjugate base and acid for the indicator are inversely related to each other, meaning that when the concentration of one goes up, the other will go down, and vice versa. And therefore, the color of the indicator will depend on the relative amount of each species present. In other words, the position of the equilibrium. The color is going to change over a pH range, but the actual transition point or endpoint is defined as when the concentrations of the protonated and deprotonated form are equal to each other. In other words, the transition point or endpoint is the middle of that pH range.